Hello and welcome to the next video. Okay, so we already talked about linear programming quite extensively from the previous videos. Okay, now we are moving forward to see what if I increase the production of one particular inputs. Will that change any way with my objective function? Okay, this is the example, the what if question. Okay, this is the meaning of the sensitivity analysis. All right, so in this case, just to recap back of our original problem from the previous video. Okay, we have a Giappetto problems. You can refer back to the video one, okay, to get the real question out of the problems. But more or less, okay, this is the gist of the problem. We have a maximized objective function of 3x1 plus 2x squared, and then our constraint that we need to consider is actually three. Okay, the finishing constraint, the carpentry, the demand. Okay, and then the sign restriction is just for the sake of that your valuation is in the first quadrant. Okay, that's straightforward, I think. Okay, now what happened? Okay, how can we proceed to find the if question? Okay, what if question? Okay, by using a graphical methods. Okay, so there are actually two ways to solve this problem. The first one, graphical, because it's easy for you to see it, but it does not make sense if you have lots of constraint, right? Because you need to keep track of all your constraint, and then you need to look at your iso profit level, iso profit line, or a level curve line. It does not make sense. So that's why we upgrade our methods, okay, or our solution for the methods by using another software. Okay, so I'm going to highlight a little bit more on the on the solution of the software, on the solution of using software in the next video. Okay, but for the time being, we just focus on the graphical solutions. All right. So if you notice at the lower back, lower part on the left hand side is the objective function and the constraint. Okay, I put that there so that you don't need to keep on coming back to the original problem. Okay, so let's say that is your problem, and then from the previous video you already have this graph, and then all these are all the line that is restricted line that will give you the feasible solutions in the yellow green color here, and then the level here. Okay, this is your line. Okay, your iso profit line that representing your maximum valuation. Okay, your objective functions. All right, so how to move about? All right, how to move about? Okay, all right, okay. You can see over here, if you look straightly at the constraint on your the first constraint, okay, the defining constraint. Okay, I show you previously. This is your defining constraint, right? Okay, you have the first constraint over here, your finishing constraint. This one is the most significant constraint for you to consider. Okay, this is your binding solutions. All right, so that's why you have B earlier, right, as your object optimal values that can produce your optimal solutions. All right, so in this case, if you notice over here, your finishing line over here, the slope is -2. All right, and then the slope is -2, and then from here you can see the carpentry constraint, the slope is -1. Okay, and then you can see the slope of the isoprofit line must be in between these two slope, right? Okay, it makes sense, isn't it? Because you want to know whether your isoprofit line should increase on the right hand side, okay, meaning that it will move upward, okay, so that it will get the maximum solutions, right? Okay, for example, like this one. Okay, so this is your isoprofit line. Okay, your Z. So basically, you can see over here, your slope for your isoprofit line is negative 3 over 2, which is just in between negative 1 and negative 2. All right, what does that tells you? Okay, so in this case, you can see this analysis, okay, it can determine whether the change in your RHS, meaning that your right hand side, okay, of a constraint will make the current basis no longer optimal. Okay, what does it mean that by the right hand side over here? Okay, this is what. This is all the right hand sides values over there, okay, just in case you get confused with the details. All right, so if you notice, if your value, okay, is changed, then as long as where the carpentry and finishing constraints are binding, your optimal solution will still occur. All right, because it is an intersection of a binding line, and at the same time, your feasible regions is at the bottom of them. Okay, so uh, it is still, you still will have an optimal solution no matter how you're going to change. But the question is how you're going to see the changes of your optimal solution with the changing of your line ni, okay, your constraint line. Okay, so that is the issue here. Okay, what does it mean by that? Okay, we just focus first on the first constraint. Okay, you focus your intention, okay, attention into your finishing constraint. Okay, your finishing constraint is here. Okay, this is your original finishing constraint. Okay, and then you start to look at two different finishing constraint. Okay, the first one is this one. Okay, you can double check on the dotted line there. Okay, and the second one is on this one. Okay, you can see over here it changes a little bit between 80 and also 120, and see how it goes. Okay, look at my first point there. It mentioned that in this problem, okay, if let's say, okay, it makes some situational issues here. If let's say my value of b, okay, b is your, remember, b is your right hand side value, okay, meaning that earlier original profit line, sorry, original constraint line, you will have your b equal to 100 here. This is your original value. And then if let's say you have b which is 120 over. Okay, 120 over, meaning that this 120 over is this line. Okay, if you put like that, it should be in the 120. But what happened if let's say you have greater than 120 over, meaning that, oops, okay, you violate the situational behavior where you have this constraint D. Okay, constraint D is for your demand constraint. All right, your demand constraint is here, this one. This one. You violate this because once you exceed this value, meaning that let's say your line is over here, then it is not in this region anymore, right? Even though you can put your feasible, okay, don't forget, once you put this one over here, your feasible region now becomes like this. Your yellow line is a little bit greater than the previous yellow line here, but it can never exceed this value, right, over here, because you have the limitation whereby this is no longer your constraint anymore. It is a limitation of your constraint. So by the end of the day, the most value for your finishing constraint should be less than 120. Makes sense, right? Okay, by using the same principle, okay, you also need to look at the limiting values, okay, for your right hand side value for the first constraint at the lower bottom. Okay, the lower bottom meaning that this one. Why you choose 80 over here? Okay, you look carefully. The same thing applies there. If let's say you put this one, Okay, sorry. If let's say you put this one, okay, and if let's say your line is less than this one, meaning that your value over here should be uh, this one. Where is it? Okay, this one. This statement. Your x1 now will be less than 0. Okay, your value now should be somewhere over here. Okay, remember x1, right? X1, your value should be somewhere over here, whereas our intention is that we just focus on the first quadrant, right? On the first quadrant, so your non-negativity constraint will be violated. That also does not make sense, right? Okay, that is why we state our constraint. Okay, we not a constraint, we state our flexibility of our values on the right hand side for the first constraint, in between 80 to 120 over here. All right, so that is that makes sense, right? That makes sense. Okay, so if you have this current basis ni, okay, if your right hand side value is over here, your now you look at your decision variables value. Okay, decision, what is decision variable? Always remember your decision variable. Okay, it's a little bit messy here, but at least you get the understanding of it a little bit better. This is your decision values, all right? So if you change your constraint, by right, it makes sense. All right, you can expect that you will need to also, the variable value will also be changing, and also once your variable value change, then by right your z should change also, right? Okay, so that is the scenario where the sensitivity analysis took place. Okay, so this is how it is. All right, so this, okay, this delta, I just call this a delta, right? Easier to easier for you to get. Okay, this delta is actually the additional change, okay, to your finishing constraint, right? Just now. Okay, and then if let's say you put the delta over here, okay, assuming you put the delta, you plus the delta there, and then you can sense if you put extra delta here, by right your x1 should be plus delta and your x2 should be minus delta. Okay, make sense? If you don't get it again, okay, I go back to this original value. If let's say this is your line, okay, we are looking at this line, okay, we start with 100. If let's say I plus 100 with my delta, meaning that plus delta, meaning that the distance over here increasing. All right, so once it is increasing, by right you should expect your point now should shift from B to this value, right? Okay, and you can imagine once it is shifted into this value, meaning that your x1 should shift plus. Okay, your x1 should shift. Okay, whereas your x2 is on your vertical line, your x2 should shift decreasingly, okay, meaning that is it will move downward. All right, so that's why you have x1 plus delta, for example, and x2 minus delta. That's why you have this. Okay, and then once you make sense with this one, the z function is easy. Okay, meaning that easy, why? Because you just plug in using your algebra knowledge. Okay, meaning that your z equal to 3x1, so your x1 now becomes this one, and then your x2 now becomes that one, and then your final solution for your z now, the changes of your z is just solving and simplifying your evaluation on the one after you take into account your delta. That is what you get. All right, so Meaning that in that case, you can simplify it in this term. Okay, as long as your current basis remain optimal. Okay, if you consider a 1 unit increase, okay, we cannot consider for the sake of our argument over here, we consider one by one, all right, increase. So a 1 unit increase in the number of finishing hours will increase your optimal Z by another one ringgit. Okay, so that is the concept of sensitivity analysis. Okay, so basically this is just the overall idea, overall idea of what I have mentioned earlier. Okay, so I start with this one. This is the one where I'm going to bridge this video to the next video. Okay, so this video is a little bit tricky, right? Because you have to keep looking back and forth with your shadow, okay, shadow of the movement of your constraint. Okay, you identify the constraint first, and then you look. Okay, what happened if you increase one, and then if you decrease one, and then you see the shadow of it, and you find the other concept of sensitivity analysis. But normally you can cut short your operation on your graphical situation, especially if your constraint is a lot, and especially if your variable is a lot. Okay, so how to simplify this problem, but you still able to calculate this sensitivity? You still have some idea of the your optimal solution is where, and then what happened to your variables. Okay, but in a more easier way for you to solve. Okay, so that is when machine took place. All right, machine meaning that you can always use software. So in this case, I'm going to show you just one example of using a QM for Windows software. Okay, it's cheap, and then it's just a straightforward situation, and then you can get lots of benefit from that. All right, so I leave you with this one first, okay, before we proceed to the next video on the QM for window DIY. All right, all the best, and I'll see you soon.